Good afternoon. Our team is presenting a senior project on the topic Alleviate collisions in LoRa networks using reinforcement learning. Here's our agenda for today. Here you may see the definition for Internet of Things. What is LoRa? Long-range networks are wireless communication systems designed for long-range, low power, and low data rate connectivity. They are ideal for IoT applications, where devices need to send small chunks of data over large distances while saving battery life. These networks usually use Aloha-style medium access protocols. Medium access protocols decide how and when devices take turns to send data over a shared network. Here you may see illustration of packet collision. For example, imagine you are in a room with 100 people, and everyone wants to talk using the same microphone. No one raises their hand, they just speak randomly whenever they want to. Sometimes two people talk at the same time, and their voices, of course, clash, and no one is heard clearly. In that case, packet collision happens. This is how Aloha works. Also, it is simple to implement protocol. They have disadvantages such as frequent collisions and a lower packet delivery ratio, PDR. It is the percentage of packets that successfully arrive from end devices to gateway. Because of such frequent collisions, more packets are getting lost, delayed, or corrupted. Overall, this results in decreased performance. Therefore, our research goal is to explore adaptive methods like reinforcement learning, where devices may learn from their past experiences to make better decisions over time. So, our ultimate goal is to make communication more efficient, even when the network is crowded. Next is project overview. What have we developed so far? We developed a SARSA-based reinforcement learning agent that learns to choose optimal time slots based on their past experiences, minimize collisions, and maximize successful transmissions over time. That affects on PDR. Key components we developed. First, a slotted time model where time is divided into fixed pieces so device can pick a specific time slot to transmit their data. Second, we used Q-learning SARSA algorithm. And third, we added minimum heap priority queue to make the system faster and smarter decisions.
We implemented a testbed to easily conduct experiments on our algorithm. The testbed consists of 15 ESP32 devices that act as end devices. Those are the devices that send packets. There is one gateway that receives those packets and a Raspberry Pi server that controls the experiment. The server allows flexible control over the experiment and gives easy access to devices, parameters, or Wi-Fi. The experiment flows consist of 3 stages. The first stage is automatic. During the starting stage, devices are assigned to their static IPs and the firmware gets uploaded. The second stage is initialized by the server. When the server sends a signal to devices to start the experiment, it can pass information such as parameters, values, and gateway address. The devices then begin the LoRa transmission. At the end of the experiment, devices send their statistics to the server. The server parses the data and produces the result of the experiment. The process can be repeated if needed. To implement our SARSA solution, we had to redesign the packet transmission protocol. Instead of waiting random periods of time, like Aloha does, we divided time into slots. Each device chooses a slot and sends its packets into the appropriate time window. This approach is more consistent and controllable and allows SARSA to easily time its deliveries. Here we see the SARSA algorithm formula and our implementation. To explain it in simple terms, each device assigns a certain score to every time slot. The device chooses the time slot and we chooses the time slot with the highest score, and depending on whether the transmission was successful or not, the score will be increased or decreased. The device then only tries to choose a time slot that it thinks is unoccupied. After all time slots pass, the process repeats.
And now let's look at one of the key results. And now also I want to point that all data are from real hardware, and you can see the hardware after the main part of the presentation. And in the graph, we compare SARSA with two common protocols, with pure aloha and slotted aloha. And you can see that results are clear that SARSA consistently performs better, even when the network is busy with up to 15 devices active at the same time. The biggest improvement we saw when there were 9 devices. SARSA improved packet delivery by 22.5% over slotted aloha and by 36% over pure aloha. It's a big evidence that SARS is reliable, especially in real-world networks where every loss of packet can mean loss of data. And in the next slide, you can see that we successfully achieved our goal. We built an open source testbed using MicroPython that anyone can use for future research and experiments with LoRa WAN networks. It's simple and low cost and flexible. Moreover, on top of that, we showed that SARS, our model, is actually useful in real world. This means device can learn over time to send data and avoid collisions. And for future work, it would be nice to see the scalability and large-scale deployment. We can see that our research can focus on extending the evaluation to larger networks to examine the system performance under heavy load. We also can see how hybrid models approaches might offer new strategies where RL dynamically adapts the network under varying traffic conditions, while traditional methods provide a standard behavior for well-understood scenarios. Also, investigating distributed learning schemes where each device learns independently or shares partial information could reduce communication overhead and enhance scalability. And in conclusion, I want to say that to solve this problem, to solve our research problem, we built a working open source testbed using MicroPython. This means anyone can use it in the future to test their own ideas. And I want to say that we're proud to show that smart on-device learning really works and can be useful for real-world IoT systems. And finally, I would like to thank our supervisor for his continuous support and guidance. Thank you for your attention. Here you can see reference list. In the center of the setup, we have a Raspberry Pi connected to a monitor and keyboard, acting as a control hub. The Raspberry Pi is also connected to one ESP32 device, which serves as a LoRa gateway. To start an experiment, we simply launch a Python script from the terminal on the monitor. The script handles two key tasks. It broadcasts the experiment configuration to all end devices over Wi-Fi and begins logging serial data from the gateway. Once the device receives the start signal, they begin their transmission cycles according to the selected protocol. Here you can see one of 15 ESP32S3 microcontrollers, which serve as an end device in the network. Each ESP32 device is equipped with an NSX1262 LoRa transceiver module. Each device was grouped and physically distributed across different locations within our lab environment to simulate realistic deployment scenario. In the setup, all devices remained in standby state, actively waiting for command from central server to begin the transmission cycle.